All right, so we've got a two-part problem. We want to find the general solution to this differential equation and then sketch the face plane. Okay, so we'll do the face plane on the, oh, I didn't give myself enough room, so this might be fun. Might have to do this in 2 videos, we'll see. So I'm going to start by finding, so on the exam, on the question like this, you'll have an extra page. Okay, so first we want to find the eigenvalues and eigenvectors. So we're going to look at the determinant of 3 minus lambda minus 2, 4 minus 1 minus lambda. This is equal to lambda plus 1 times lambda minus 3 plus 8. Okay, this is going to be lambda squared minus 3 lambda plus 2 lambda. So minus 2 lambda minus 3 plus 8. So plus 5, and I want to set this equal to 0. And just to solve for lambda, we could either try to factor, which I'll just tell you in this case you're not able to. You can just think about it for a little bit. So now we need to solve for lambda, and I like to do this by completing the square. So this is lambda minus 1 squared minus 1 plus 5, so it ends up being plus 4. And so we get that we have complex eigenvalues. Lambda 1 and 2 are going to be equal to 1 plus or minus 2i. Okay, so we know we've got complex eigenvalues. Now we want to find the corresponding eigenvectors. So we're going to look at the equation 3 minus 1 plus 2i minus 2 minus 4 minus 1 minus 1 plus 2i times xy. Set this equal to 0, 0. Okay, so notice the top equation, 3 minus 1 is 2. So this is 2 minus 2ix minus 2y is equal to 0. And in the bottom, we have minus 4x. Okay, minus 1 minus, so this is going to be, so we've got minus 1 minus 1. So we'll write plus minus 2 minus 2iy is equal to 0. Okay, and just so as a check, notice that if you multiply the top equation by minus 1 plus I, you get the bottom equation. Okay, this is a check we like to make just to make sure we pick the right eigenvalues and eigenvectors and have done everything correctly. It's a little difficult to see how to do this when we have complex numbers, but it's fine. Anyways, so what this tells us, we're going to solve the easiest equation. I think that's the top one, and this tells us that y is equal to, so if I add 2y to both sides and divide both sides by 2, I get y is equal to 1 minus ix. Okay, so any vector where the top entry is 1 minus I times the bottom entry, or sorry, any vector where the bottom entry is 1 minus I times the top entry, except for the 0 vector, is going to be an eigenvector. So something like this. Okay, all right, now remember to find the general solution. We write this, so the general solution is going to be C1 times the real part of e to the lambda t v plus C2 times the imaginary part of e to the lambda t v. Okay, so now we need to find the real and imaginary part of e to the lambda t v. And to do that, remember, we use Euler's formula. So let me erase all of this. Okay, so we have e to the 1 plus 2it times 1 minus I. We're going to split both of these into the real and imaginary parts. So I'll have an e to the t that's just going to basically multiply everything. And then e to the 2it is cosine 2t plus I sine 2t, and then plus, we'll split the, then we'll multiply this, not plus, we'll multiply this by the vector, which is going to be 1, 1 plus I 0 minus 1. Like this. Okay? And now we're going to out of room. Hold on, let me just shift the frame down. Hold on. Okay, there we go. Little technical issues. Really wish I'd put an extra page here. Okay, so now this is e to the t Okay, what's the real part going to be? How do we get a real part? Well, it's going to be cosine 2t times 1, 1, or I sine of 2t times the imaginary vector here. But notice what's going to happen. I times I is minus 1, and we're multiplying it by minus 1. Okay, so I times I is minus 1 times minus 1 is 1. So the real part of the vector is going to be cosine 2t and then cosine 2t plus sine 2t. Okay, and then the imaginary part of the vector is going to be plus I times e to the t. How do we get an imaginary part? Well, we could do cosine of 2t times I 0 minus 1, or sine of 2t, I sine of 2t times 1, 1. So we'll get sine 2t and then minus cosine 2t plus sine of 2t. Okay, now let me take so what this tells us then is that the general solution is c1 e to the t cosine 2t cosine 2t plus sine 2t plus c2 e to the t sine 2t minus cosine 2t plus sine 2t, like this. Okay, now I'm basically just going to copy this in the line above it so I can draw the phase plane. Okay, so now I want to draw the phase plane. So let me first start by drawing the axes like this. Okay, so whenever we have a trigonometric thing, like when we have complex eigenvalues, we know that it's either going to be, the phase plane is either going to be, the solutions in the phase plane are either going to be, ellipses or spirals. If the real part is 0, we'll have ellipses. So if the real part of the eigenvalue is 0, we'll have ellipses. If it's not, it'll be spirals. If the real part is positive, the spirals will be going away from the origin. If the real part is negative, the spirals will be going into the origin. And now I just need to know whether they're going to be going counterclockwise or clockwise. And the way we do that, we're going to compute the tangent vector at the point 1, 0. So we want to look at the tangent vector for the curve that passes through 1, 0. And the way we do that is we just multiply. We know, so the tangent vector is just the derivative of the curve. Okay, and the solution curve are just solutions to the differential equation. So all I'm going to do is multiply the matrix 3 minus 2, 4 minus 1 by 1, 0, and we get 3, 4. Okay, and this tells us that the tangent vector through the point 1, 0 is going to be going roughly in this direction. Okay, and so what this means is the spirals are going away from the origin in the counterclockwise direction because the curve that comes through the point 1, 0 is going to be going like this. Okay, and then if we kind of go back to in negative infinity, time is going to be like this, and as t goes to minus infinity, it'll spiral infinitely many times around the origin. But anyways, this is the phase plane. Sorry everything is kind of squished. If you can't see it very well here on the YouTube video, just look at the copy of this that I'm uploading to my webpage. Yeah, it's a little difficult to see because I didn't add another page here, but on the exam you'll have another page to use.